Hi everyone, so in this video, I want to continue with where we left off talking about statistical experiments, sample spaces, and events. So one special relationship between a pair of events. Let's consider two events, A and B. We would say that these two events are disjoint. We also would say that they're mutually exclusive. We can use these two terms interchangeably if those two events cannot occur at the same time. So in other words, there are not any outcomes that would be in both event A and event B. So the intersection of these two events is therefore going to be the empty set. And so to motivate this concept, let's consider the following example. So let's say a university has a total of 1,000 undergraduate students. And we are going to pick an undergraduate student at random from this population. So let's let M denote the event that the student is a math major. E would be that the student is an economics major. F is that the student is a freshman. J denotes the event that this randomly selected student is a junior. And now let's consider the following pairs of events. And for each of these pairs, let's consider whether or not these two events would be disjoint, mutually exclusive events. So for number one, we have M and J. So we pick a student. Is it possible that they fall into both the event that they are a math major and the event that they are a junior? And the answer here is it would make sense that it is possible for a student, a math major, to be a junior. So since these two events are possible to occur at the same time, then we would say that they are not disjoint. Since if they are disjoint, then there can't be anything in their intersection. So any student that is a junior and a math major would sit in the intersection. In number two, we have F and J. So is it possible that we pick a student and they are a freshman and that they are a junior? Well, that wouldn't be possible. So since it's not possible for these two events to occur at the same time, then these two events are disjoint. They are mutually exclusive. And for the last one, events M and E, let's consider those two. And so is it possible for a student to major in mathematics and major in economics? And since it is possible to declare two majors, you can double major. It is possible that there would be a student that would fall into both of those sets, math major and economics major. So since these can occur at the same time, we would say that these two events are not disjoint from each other. And so now for finite sample spaces, such as our example with the 1,000 undergraduate students at a university, we can use simple counting techniques to determine probabilities. So we usually use this notation P of A to denote what is the probability that this event A occurs. And so if we assume that each outcome in the sample space is equally likely, so in other words, we have an equally likely chance of picking any one student out of the population of all students, then we can calculate these probabilities simply by counting up how many outcomes fall in event A out of the total number of outcomes in the entire sample space omega. So we use this notation in mathematics that looks like the absolute value. This denotes the number of outcomes in event A, and this would denote the number of outcomes in the sample space omega. So let's take a very simple example to start with, just building off of the previous example where we have a university with 1,000 undergraduate students. And let's say we know that there are 50 math majors and 40 econ majors at this university. And again, M and E are going to refer to the event that when we pick a random student, they would be either a math major or, in this case, an econ major would be E. So here we would like to calculate and interpret the meaning of the following probability. So in one, we've got what is the probability of M, P of M. So this would be saying what is the probability if we pick a student at random that that student would be a math major? And we can calculate this by taking what are the total number of math majors, which are 50. So this is the number of outcomes in M over the total sample space of 1,000 students. So this would give us a 0.05. So in other words, 5% of the students are math majors. And to calculate too, what's the probability that a randomly selected student is an econ major? Well, we have 40 econ majors out of 1,000 undergraduates. So that would give us 0.04. And we can interpret that as saying, well, 4% of all undergrads are majoring in economics. And so the previous example looked at the probability of a single event, a simple probability. What is the probability that they are majoring in math? So there was only one event we were considering. When oftentimes you want to consider a combination of events. We already thought about that when we were considering a pair of events and whether they were disjoint or not. So we can also consider what is the probability of some combination of events M and E. So sticking with the same example, we've got 1,000 undergraduate students at this university. 50 are math majors, 40 are econ majors. And here we've got this additional information that included in these totals are 10 students that are double majors. So what I mean by that are we have these 50 math majors, 10 out of those 50 math majors are also majoring in econ. So let's calculate and interpret the following two combination of events. So number one is saying what is the probability that M, and remember when we have this upside down symbol here, this is the intersection. So this is saying what's the probability that both events M and event E occur at the same time. And so to calculate this, we don't need to change our approach. The probability of M intersect E would just be how many outcomes occur in both M and E divided by the total number of outcomes in the sample space. So we have 10 students that were both math and economics majors out of the 1,000 undergraduate students. So this would tell us that 1% of all students at the university are double majoring in math and econ. And in 2, it looks very similar. This frown over here, this intersection symbol got flipped into a smile, right? And now we've got this union symbol. So M union E means they are a math major or an economics major. So this is an or situation. And so when we calculate this probability, we need to be careful because if I just simply say, well, let's count up how many outcomes, how many students are math or econ majors, and divide by the total number of students, we don't want to do any double counting since some students are both math and econ majors. So we can count up the total number of math majors. We can add up the total number of econ majors, but then we want to take into account that the double majors we already counted in the math group. So we don't want to double count math, econ double majors. So then we subtract the total number of students that were both math and econ majors. And then we divide all of that by the total number of students. So that gives us the number of math majors was 50, econ majors was 40, but there were 10 double majors that we don't want to double count. So we subtract that in the numerator, and then we divide by the 1,000. And so in this case, that gives us a total of 80 students out of the 1,000, which is 8%. So that tells us that 8% of the students at this university are majoring in either math or in economics. And so it's worth pointing out by properties of addition and fractions, right, we can break up this fraction and we could have equivalently calculated this probability by saying what's the probability that a student is the math major, the 50 out of 1,000, plus the probability that they're an econ major, that's the 40 out of 1,000, and then subtract the probability that the student is a math and an econ double major. So this is a common way that we could calculate this probability as well. And so lastly, let's just generalize the result from the previous example. When we want to calculate the probability that events A or B occur, we can use what's called the additive rule, which is we can calculate the probability that event A occurs, add what is the probability that event B occurs, and then we want to avoid any double counting. And so that's why we would subtract the probability that events A and B both occur. And so to come back to where we started in this video, recall that if in the special case that these two events, A and B, are disjoint or mutually exclusive, then that means event A and B can't occur at the same time. They don't share any outcomes. And as a result of that, then we know that the probability that A intersect B has to be 0, since there are no outcomes that satisfy A and B. And so in this special case, and only in this case, when the events are mutually exclusive, then the probability of A or B, the probability of A union B, is simply the probability of A plus the probability of B. We can simply just add them. But more generally speaking, be very, very careful. We cannot do that unless we're sure that those two events can't occur at the same time.